Welcome to the Origins Podcast. I'm your host, Lawrence Krauss, and this is one of my favorite segments of the Origins Podcast, where I get to spend an hour with Sabine Hossenfelder, and we get to talk about what's new in science and critique, hype, talk about things that are exciting, and generally sometimes agree and often disagree. But today we'll see. And I want to give Sabine the first chance, and I think Sabine wants to talk first about a new result having to do with lumpy wormholes, whatever they are.
Yeah, kind of. So it's a combination of hype and critique, I guess. So I've noticed, like, this is a more general theme that I've noticed in the past year or something, that there are a lot of headlines about wormholes. And that didn't used to be the case. Like, wormholes used to be this really fringe thing. No one really wanted to talk about it. And now it's become more accepted. So I thought it'd be good that we talk about this a little bit. I think it was kicked off by this wormhole in a quantum computer story from a couple of years ago. And so suddenly other physicists dared to write papers about wormholes. So, for example, one of the headlines that I saw like 2 months ago or something was that one of the signals that has been interpreted as a black hole merger, like gravitational wave signal from a black hole merger, might actually have been a merger with a wormhole. And then the next story is this thing with the lumpy wormholes that you mentioned. You know, wormholes aren't just smooth kind of tube, the way that they're typically pictured, but they have quantum effects and that makes them lumpy. And another story that I read is that dark energy is actually made of teeny tiny wormholes, and they're all around us. And actually entanglement is a type of wormhole, and so on. So, and I think that there are two different things going on. So the one thing is that wormholes are actually a solution of Einstein's field equations. Like, technically, you can write them down. The best known example is probably the Einstein-Rosen bridge. That's been known for 90 years or something, like 35 or something. So they exist. And there are other types of wormholes that people have played with. They all have the same problem, which is that you need some sort of negative energy to keep them open. Otherwise, they'll collapse. And no one really knows how to create them. Like, this is like an unknown issue. Like, you can write down a solution, all right, like it exists for all time, but it also means that it has to have been there since the beginning of the universe. So no one knows how to actually create a wormhole that connects to different places. Okay, but mathematically...
Let me interrupt for 1 second. It's really important that those wormholes, that they have negative energy, because one of my favorite early results from Kip Thorne was that if there is just a single wormhole in the universe, then you can make a time machine. So that's why that's one of the reasons why I'm pretty sure there are no wormholes in the universe. But anyway, go on.
Oh, well, so, this is because, like, whenever you can connect two places in space, you can move one of them back in time. So, so then it looks like you can go back in time. Like, personally, I think you can rule this sort of thing out by relying on entropy increase, so that one direction of the wormhole wouldn't be possible to travel. But it still doesn't solve the problem of the negative energy. So wormholes have like loads of theoretical problems. Whatever.
And we should say for people listening, that these are theoretical constructs in general relativity, but there's no evidence of any existing wormholes, just in case people are wondering.
Well, maybe the gravitational wave signal was the evidence. Like, if you read the headlines, you might actually get away with the idea. Like, what they did was they looked at the signal of the gravitational waves, and then they compared what you'd get from a black hole merger and from a merger of a black hole with a wormhole. And what they found, I thought this was quite amusing, was that actually the black hole merger fits better to the signal, like very slightly better. Yeah, and I would say, like, statistically they were both, quite similar, and that is like a typical thing. Like, basically, from any signal that you see from the outside, you can't distinguish the two things. So I think it's fine that they did this analysis. And even though they didn't find anything conclusive, they put it out, and this is all well and good. I just think that the people who wrote articles about it could have been a little clearer about what they didn't find, basically. And so this is the one side where people are looking at actually astrophysical observations, and they're trying to figure out, could it be a wormhole? And typically the answer is there's no way we can tell these two apart. So why are we even asking the question? But the other thing that's going on, and this is where the story with the wormhole in the quantum computer comes from, is that they're being used as a sort of mathematical tool to actually understand quantum effects. So this is where this idea comes from, that entanglement can be understood as a type of wormhole, in an abstract sense.
Yeah.
And again, I'm not against this. This is fine with me. You using the mathematics in a new way, and that might give you new ways of thinking about it. That might give us some progress in understanding quantum theory, or maybe general relativity, or both. But again, it is somewhat unclear if you read the headlines. This is a mathematical tool. This was the entire issue with this worm on a quantum computer story. And the thing with the lumpy wormholes is kind of the same type. If you're trying to describe this quantum link that is entanglement, so to speak, somehow, then now it has these quantum fluctuations, so it's not actually a smooth thing. Okay, fine. What do we learn from this? I'm actually not sure. Maybe they'll have to think about it somewhat more. Somewhat I wonder, why does the thing, this is a super, super mathematically heavy paper. Why does something like this make headlines? And I think it's just because the word wormhole kept attention. And then there's this story about the dark energy. Is dark energy actually made up of teeny tiny wormholes that are all around us? Somewhat embarrassingly, I have to admit, I once wrote a paper about something very similar. I didn't call it wormholes. I called it, I called it.
I was shaking my head. I'm sorry I did, but
and so the thing is, you can basically, the only thing you need the density of these things to fit to the way that dark energy behaves, which is that it doesn't dilute. And so this is the only thing you need, and then you can make it work. So it's kind of an empty model, basically. This is why I stopped working on it, because you can make it fit anything, like dark matter, dark energy, whatever. You just have to get the distribution right, which is kind of obvious if you think about it, right? So basically, this is my summary of the situation. But I find it from a community perspective, I find it very interesting. It's a similar thing with warp drives that we talked about, I think, last month. That people, they dare to think about it, and generally, I think this is a good thing. So, people are getting more open-minded. But it has this downside that the popular science press picks up on it and doesn't give you the context that you need.
Do you think that I worry about it, because I think that for precisely that reason, that if you mention wormholes, even if there aren't real wormholes, in fact, there were so many critiques of the Fermilab work that it was somehow exploring a multiverse and there were wormholes, when in fact it was a very simple kind of demonstration, but a simple quantum computer calculation, that people are encouraged. Do you think people are encouraged to work on it because they think if they mention wormhole in their paper, they're going to get noticed?
Some of them certainly. You could really see this after the thing with the wormhole and quantum computer. 1 or 2 months later, there was this bulge of papers about wormholes with press releases. So I think it certainly affects what people consider to be press release worthy.
Yeah. And one should say that the kind of wormholes that people are talking about in the context of this quantum gravity stuff are generally kind of virtual. They're not real ones that are hanging out in space. They're virtual. They're basically virtual mathematical solutions to describe intermediate quantum states that may or may not do something of interest, basically. They're not real wormholes that Jodie Foster can go in and see aliens or anything like that.
Yes. So basically, if you actually look at the paper and you look at what they've actually done, usually it's disappointing.
Okay. Well, from the land of speculation to at least a little bit of reality, not earth-shattering, but nevertheless, it's kind of nice and frustrating at the same time. As we talk about, the standard model of particle physics works frustratingly well, and we keep looking for something where it breaks down. And this recent report from CERN, from one of the two large detectors, the Atlas detector, sees the Higgs particle decay into muon anti-muon pair. Now that doesn't sound particularly exciting a priori, but what it does is actually it follows up on a result reported earlier by the other competing experiment, the CMS experiment, which found this result at 3 sigma, which is like 99%, 99.9%, I guess, likely, and they've increased it to 3.4 sigma. But the interesting thing is, the Higgs has discovered one of the properties of the Higgs that makes it so exciting, besides the fact that it's a central feature of the standard model allowing the mathematics to work, is that it in principle gives mass to most elementary particles. And it does that, interestingly, in the model, that the heavier particles couple more strongly to the Higgs, and the lighter particles couple less strongly to the Higgs. And so the mass you get depends upon how strong you are coupled to the Higgs particles. And if this is the case, if you create Higgs particles and they can decay, you'd expect them to see them decay most of the time to heavy particles, because they're coupled more strongly to heavy particles, and much less often to light particles. That means it's much more difficult to look for Higgs decays to light particles, because they happen very rarely. But if you can check that it happens, and if you can check that the ratio of such decays is in the ratio of masses, it confirms that central feature of the standard model, and that's why people have been looking for it. And as I say, CMS claimed to see a result, and now the Atlas experiment sees that result. And it probably happens 1,000 or 10,000 times less often than the decay to heavier quarks, and it appears to be consistent with standard model, which means that this remarkably simple idea that I never really believed early 40 years ago, it just seemed too simple to be true, that particles get mass by the strength of their coupling to this one particle nature, actually seems to be true. Nature seems to be remarkably simple in that way, and it works. So this simply confirms the standard model, but it is nice and still remarkable, to me at least, that this simple idea seems to be true, and they confirm it to 3.4 sigma. As you know, in particle physics, we like to have 5 sigma results to get something that we can claim as gold. In medicine, it's 1 sigma, and in at the 90% or 68% confidence level. But in particle physics, where you have millions and millions and millions of events, you like to show the statistics is good enough. This is pretty good. You can see in the paper that you can actually see fit. You don't even need the statistics to see the bump where it decays into these things. And so it's nothing earth-shattering, but it is interesting to see the standard model works, and to me, remarkable in that sense that that nature seems to be that simple. What do you think?
Yeah, definitely. I mean, so the origin of mass is kind of one of the, I guess, the big mysteries, you could almost say, of particle physics, and that confirms that it actually works the way that we think it works. It's also, like, I find it a little bit frustrating, because where you really want to know where the masses come from are the neutrinos, and they won't be able to measure this at the LHC.
Yeah.
And so you know this, of course, but for other people who are listening, the issue with the neutrinos is that to make this work, this mechanism of mass generation, you need a right-handed and a left-handed particle. And from the neutrinos, we've only ever observed the left-handed version. So what gives? Like, either there are right-handed neutrinos somewhere, but we've never seen one, or the mechanism of mass generation for the neutrinos actually has to work differently. And so this is why the masses of the neutrinos are so super interesting. And this is also why a lot of particle physicists, and I've had endless arguments about this, actually say that the neutrino masses are evidence of physics beyond the standard model. And we can argue about whether this makes sense or not, but there's a rationale for this, which is that we either need this new particle or we need a new mechanism. Something else has to be there. But kind of frustratingly enough, like the energy scale at which you'd be able to figure this out, like, well, we should be seeing these new particles, for example, like this is one of the solutions, is like 10 orders of magnitude or something beyond the Large Hadron Collider. So,
Yeah, it's
I mean,
unfortunate.
this,
But I do think that the neutrino, it's interesting and frustrating at the same time. Neutrino masses, I would argue, are evidence of the standard model, because the standard model doesn't have right-hand neutrinos, and if you do the other mechanism, it doesn't have what's called lepton number violation, which is the other way to do it. So the only way you can neutrino mass is to add something to standard model. What's frustrating about it, though, is you can add something that basically has no impact on the rest of the standard model, so it sort of hangs out there on its own. And what we really want is something that shows some central feature of the standard model is wrong or needs to be corrected. So it's evidence of something new, but it's something new that's out there that unfortunately could remain hidden and not impact on any other sectors of the standard model, and at least in an experimentally accessible way. So it's fascinating but frustrating at the same time.
Yeah, I guess one could argue, though, that the right-handed neutrinos are part of the standard model, like all the other right-handed particles that belong to the quarks and so on and so forth. And in this sense, it wouldn't be physics beyond the standard model. But this is why I say, like, it's kind of a pointless argument. This is why physicists obsessed about the masses of neutrinos.
It's certainly nice to see that it's working and that this strange feature seems to be true. I as I say, and it's also an experimental, not quite a tour de force, but it's very, very difficult, and it's amazing they can do it. And of course, if we want to learn more, we might want to build a bigger collider, but China apparently has decided they don't want to do it. So why don't you take over from that?
Yeah, right. So I let me be honest, I was a little bit surprised about this, because I've been following this discussion like for 5-6 years or something.
Yeah.
So particle physicists really want to build a bigger collider, like that'll reach energies beyond that of the Large Hadron Collider. So the Large Hadron Collider, like the energy in the proton-proton collisions, like it tops out at something like 14 tera-electron volts.
Yes.
So and at the moment, the way to go to higher energies is just to build a bigger thing. I mean, we can push the magnets a little bit further because the technology has improved.
Yeah.
Basically, you have to build a bigger collider. And CERN has plans for doing this. They call it the Future Circular Collider, FCC. And it's a ring of with a circumference of something like 91 kilometers or something.
And anyway, it's huge. I mean, it would go all the way around Geneva and up and under the mountains, etc.
Yeah. So it's a huge project, and the Chinese have a very similar proposal for something that's called the Circular Electron-Positron Collider or something like that. So both of them are like two-stage projects. Like so there's a lower energy first phase, and then there's the fourth thing. And both the Chinese one, I think that it'd have a circumference of 100 kilometers. So this is kind of a comparable size. They'd reach a collision energy of about 100 tera-electron volts. So that's about a factor 6 or something, give or take some some details, about a factor 6 more than what the LHC can reach. And the hope is, of course, that the thing would discover something new. But as we've just seen, like really where you would expect the next physics to come, that's actually the neutrino masses. So this is like 10 orders of magnitude away. And then beyond this, there's quantum gravity, of course, and that's still like, I think, 2 orders of magnitude further. And somewhere in between, there's grand unification, which may or may not be actually a real thing. But so between the standard model stuff that we've tested at the Large Hadron Collider and these neutrino masses, grand unification, Planck energy scale, there's what's been called the desert. Like there's no reason to think there's anything there. Of course, physicists hope there might be something there, like dark matter or something, but there's no particular reason.
Before we talk about China, let me just jump into it to at least disagree a little bit, in the sense that we still don't understand this remarkable fact that the scale that the Large Hadron Collider looks at, where the Higgs exists, which is the scale where the sort of the weak interaction physics becomes important. Why it's 14 orders of magnitude smaller, or even more, 16 orders of magnitude smaller than the scale of gravity, when why that huge desert exists. And so I think a lot of people, myself included, assume that maybe there's some important physics that tell us why that scale is the way it is. And that's not a trivial issue, because it's the fact that that scale exists determines all of the properties of the observed universe. So, it's a mystery. And of course, it's a shot in the dark, and it's a very expensive shot in the dark, as you'll probably point out in a moment. But it's not. I don't think it's unreal. I don't think it's completely unrealistic to hope that there's something new and exciting that'll explain that otherwise totally inexplicable fact about nature. Do you disagree?
Yeah, I've written an entire book explaining why I disagree with that.
I think I wrote.
Yeah,
I wrote
basically, my point of view is, well, why not? Like, why would these scales be any different? Like, there's no reason. It might just be that this is the way that nature works. That's that. In any case,
you never know until you look, right? That's the problem. You never know until you look. And the question is worth looking.
This is like of course I get this. Like in an ideal world, we're building all the experiments that we could possibly build, and my perspective on this has always been, okay, but we don't live in that world, right? We have to make decisions. What's the next experiment that we should build? And I feel like at the present time, like building this bigger collider is not the right thing to do.
The Chinese apparently agree with you. This is what you
well,
the story,
so
right?
the last time I heard something from the Chinese process, like they like the Chinese government makes these 5-year plans, and they just made the next 5-year plan for 2026 to 2030. It just came out, and they did not select this bigger collider project, which surprised me because I saw some slides from a presentation from people from the Chinese proposal group, where they were quite confident. Like, it was looking really good. They were confident that it would be on the next 5-year plan, but it wasn't. Instead, the Chinese government went for a smaller circular collider, like something with Tau Charm collider thing, whatever. I forgot, it's one of these acronyms, at a collision energy of in the range of a few giga electron volts. So this is like a factor 10,000 less, and the thing has a circumference of 800 meters or something like this. So it's a much smaller thing, it's much cheaper. And as the name suggests, they want to use it to study the tau and the charm quark. Yeah. And so I find this an interesting development, because now the question is, of course, will the Europeans move forward with the future circular collider? So, there are two ways you can look at it. Like the one is, okay, if the Chinese had gone for the thing, that would have lowered the motivation to also build the thing in Europe, right? And so now basically the Chinese particle physicists will be very supportive of the thing in Europe. Yeah. On the other hand, you can say, well, the Chinese probably had a reason not to go forward with that, which is likely that they don't think it's particularly promising. Will it actually help the country in any particular way other than attracting particle physicists? It seems that the answer is no. It's also interesting if you look at what else is actually in their 5-year plan. It's very applied stuff. It's artificial intelligence, obviously, like quantum technologies, but also brain-computer interfaces, biotechnology. So you can basically see like where the Chinese are coming from, right? That they want to make an impact. They want to have something that has applications, and bigger collider just isn't it?
Yeah, no, I think it's of course, it's hard to know how to interpret anything the Chinese do. They're inscrutable in that regard. But you're right. I mean, it's interesting that in the article that you directed me to when you told me you're going to talk about this, of course, the Europeans are happy. They're claiming, oh, this is a good reason for us to build it. But you're right. The subtle subtext is, why did the Chinese not build it? And one of the reasons I think you're right is that maybe they decided it's not interesting. But I suspect, given the way the speed with which the Chinese seem to do things, and I'm saying this because I really think that China is already, and perhaps the dominant scientific power in the world, and will be for the rest of the century. It's the center of gravity moved from the United States. China is the new frontier for science, I think, for better or worse. And I have issues with that, but the Chinese do things so quickly. I'm wondering whether they're saying in the near term we want to have an economic impact and we want to compete with the West in all the major areas. And if we want to build a big super collider down the road, we can do it in half the time if anyone else anyway. And so the next 5-year plan or the one down the road, there's no reason to put it in now. So it's hard to know what their motivation is, I think.
Right. And so the guys who wrote the proposal say they'll resubmit it in 5 years.
In 5 years. And look, and by the way, it's worth pointing out that even that right now, I think that the LHC is good to continue till 2040, I think. So when we're talking about the next collider, we're talking 20 years down the road at least anyway. And so it's not something that's going to be built now. And many people have argued, and I have in the past, that before you make a commitment to what you're going to build, you might want to check, you might want to give the LHC the greatest possible opportunity to give a signal for what you might want to be actually looking for instead of shooting in the dark. So you might want it to run a little longer to see what directions might be fruitful and which directions are already ruled out before you actually build something. But I was surprised too, because I figured the Chinese have an infinite amount of money and could do it all. But obviously they're deciding they can't, which is interesting. To come back to colliders, there's another, actually it's a press release from another experiment in the Large Hadron Collider called the ALICE experiment, which is an experiment set up to look what's called forward of the beam, which is sort of events that happen more or less outside the core of what's producing the Higgs and all of that stuff. It's sort of ancillary, interesting physics that's either lower energy or highly rare. And they've been building that, and they've been working for a long time. And they've just produced a release saying that they have solved the mystery of light nuclei production. I didn't quite know there was a mystery, but and I read through this, and I'm not sure if it's interesting or not. I can see how it might be, but the interesting thing is, and it's interesting for the development of ultimately us. Light nuclei like deuterons, which of course are a proton and neutron, are incredibly important in the early universe as an intermediate stage, producing helium and other things, and in stars ultimately for helping the fusion process go on. But they're very fragile. They can be created because they don't need a lot of energy to create them, but they can be broken apart if there's a lot more energy very easily. And therefore, you'd think in any really high energy environment, you'd break apart deuterons and antideuterons at least as effectively as you create them, and you might not produce them. And and yet they are produced in high energy collisions, like the Large Hadron Collider, which has energies of tens or hundreds of thousands, actually much more than hundreds of thousands of times the temperatures of the sun, say. And what they discovered is, what happens, and it's not too surprising, is that in the really high energy region, they're not produced. But what happens is you produce these intermediate elementary particles, something called a delta resonance, that lasts for a trillionth of a second, which may not seem very long in our terms, but in the case of a particle physics experiment, it's long enough for that particle to get away from where all the action is, and it decays, producing protons and neutrons that then have much less energy, and by standard nuclear reactions could produce deuterons and antideuterons. So it says, even in a region where there's lots of energy and you might think you might produce these particles, you could produce intermediate states that last long enough to escape from that high energy region of where everything would be destroyed, and then to decay, and there's enough energy to produce by nuclear reactions these particles. It's not surprising. In fact, I can't imagine any other way that it would happen. But now that they've at least observed it, and maybe that's relevant for astrophysical processes where cosmic rays bombard materials and at very high energy, produce intermediate states and produce light elements that are really relevant for later on stellar energy production or something like that. So it may be interesting. I'm not sure it is, but they solved the quote unquote mystery of how it happens. And it happens, I think, in the only way you would have ever imagined it happening in the first place. And as I say, whether that's interesting or not, I don't know, but it was interesting enough for them to produce a press release. Any comments?
Well, so I don't know about this particular reaction that they observed, but I think there's a larger context here that people might be missing. So somewhat perplexingly, if you want to describe high energy collisions at the Large Hadron Collider, that's actually easier than to describe what goes on at lower energies. Like when you're looking at those nuclear energies, this is because the strong nuclear force has this strange property that's called asymptotic freedom, which means that basically the higher the energy, the simpler it becomes. And so if you're trying to figure out how a nucleus works, or why if the particles go out of the collision region, do they form color neutral states like nuclei or mesons or delta resonances or what have you? I think that's color neutral. It's got to be color neutral. So that's really, really hard to calculate. And we don't actually really understand what's going on. So on these nuclear scales, we do have effective models. Like we do have computer calculations of the different types of effective models. This is actually the sort of stuff that my husband wrote his PhD thesis on. So I know more about this than I ever wanted to do. But so it's all bottom up, right? So you try to make it work, and there's you take ingredients to make it work, basically. But from first principles, we can't really calculate it. This is also like the underlying issue with the prediction for the magnetic moment of the muon, basically. Mm-hmm. And so I think that's interesting because I want to tie this together with another headline which just came out yesterday, I think. Which is an old idea going back to actually Ed Witten in the 1980s, which is that dark matter might be a sort of quark condensate, which is we call that quark nuggets. It's a little more complicated. It's not just nuclear matter, but you also need this axion field. But the interesting thing about it is that it relies on these nuclear scale interactions that we don't really understand, and it opens this possibility that the stuff that we call dark matter might actually be made of particles we've studied like for decades. We just don't understand how they hold together. And so this is why I think these studies of the nuclear interactions, like this kind of thing and similar stuff, are actually super, super important. And people always get like that; they get flawed by, wow, we go to higher energies. But I'm well, actually, this is when we should be testing the lower energies.
Yeah, well, I think you make a really good point there, which is that it's nice to confirm fundamental theoretical predictions, but in areas where they're difficult to do, you have two choices. You either have computers or experiments, and generally nature surprises us, and it's an important regime that basically one of the only ways we can get insights into these things, that is relevant for lots of stuff, including the formation of heavy elements in neutron star in collisions of neutron stars. The stuff, as one of the things I've often talked about, which is really amazing. Do you have a gold ring on, or do you have any gold in do you wear gold at all?
Sorry.
Good. Okay. Well, people who do, it still amazes me that if you wear gold and I don't, that where does that gold come from? The only place we know in the universe it comes from is one of the weirdest things in the world, which is the collision of two neutron stars. And it's just because it's the only way we know to produce that kind of exotic nuclear reactions that are going to produce heavy elements like gold. And that was a theoretical idea. In that case, of course, it wasn't confirmed at a collider. It was confirmed in the universe when after the LIGO detector saw a collision of two neutron stars, saw the gravitational wave signature. All these telescopes looked, and unlike black holes, which are just holes in space, neutron stars have stuff, and that stuff, when it collides, produces lots of energy. and you can look at it, and telescopes of all sorts looked at it, and they actually saw the radioactive decay of basically a 1.4 Earth mass stuff that produced gold. And I found so that kind of using the universe and using colliders to try and explore this regime where we really can't do the calculations accurately is useful, and that's why Alice, I think, persists. And this particular result may not be earth-shattering, but it's nice to try and explore ideas to see, because not only that, when you observe it, it gives you empirical handles that help you build sort of tools, mathematical tools to model what's going on that might be useful for other stuff, what we call phenomenological models. Namely, they're not fundamental, but they're kludged together to reproduce the observations, and they work. And if they work, maybe those kludges will help us later on in other calculations, perform other calculations we couldn't do with the actual full underlying theory. Okay, well, from the sublime to the ridiculous, I'm not going to say it that way, but from the real to the possible, let's go back to quantum gravity and quantum mechanics and gravity. That's you have
and you just gave me the key word, which is it's a phenomenological model. So it's not actually a new theory of quantum gravity or something. It's much more modest, and I found it interesting. Because for one, I know the first author of the paper, and so we studied together, and we've been in touch ever since, because we happen to be born on exactly the same day. So every year on our birthday, we congratulate each other. So totally tangential, but just so you know, I'm somewhat of a
full disclosure.
I
like full disclosure. It's okay.
Yeah. So one of the things that I think people underestimate somewhat about general relativity is that it's a nonlinear theory, whereas quantum mechanics is a linear theory, which is in some sense it's more difficult to interpret, it's more difficult to understand, but to calculate, it's much simpler. And so one of the things that bothers me is that most of the time when we do calculations with general relativity, well, we enter a source, like it's created by particles, stars, galaxies, whatever. We basically ignore this nonlinearity. And the way that it enters is if you want to calculate anything in general relativity, you need to take an average over all those quantum things, basically. So you calculate the average. So this is kind of your classical term. And then you could use your quantum theory to calculate the uncertainty around it. And so to do these two things, you need to know how to take averages. And so what they point out in the paper is that if you look at the trajectories on which particles move, or in astrophysics you'd be interested in the trajectories on which, I don't know, stars move or whatever, then you never deal with the average of the space-time itself, so which is described by something that's called a metric tensor, but you always have some non-linear products of the metric and its derivatives. And so now the issue is that the average of the product is not the product of the averages. Yes. And basically, these guys point out that the way that one normally deals with the quantum corrections to the trajectories is that one takes the product of an average when one should be taking the average of the product. And so they redo the calculation. And they ask, like, okay, so what are the quantum corrections to the trajectories of objects in the universe if we do it correctly, in their interpretation? And they find that in the solar system doesn't make any difference, or, it makes a difference, like it's 40 orders of magnitude beyond what we can measure, the kind of thing. But they say that on cosmological scales, there is a new contribution that depends on the cosmological constant. And that isn't necessarily small. This is what they say in the press release. I'm not sure that's correct. I looked at the paper and I was like, it looks to me like it's small, but, who am I to disagree with the authors of the paper, right? So I guess we'll see about this. And the reason I find this interesting, leaving aside whether the calculation will turn out to be correct. I mean, it's published in a very good journal. I think it's PRD, if I remember correctly. It's because you remember modified Newtonian dynamics, the supposed alternative to dark matter.
Yeah.
It scales with the cosmological constant, and no one has any idea why. And so it makes such a lot of sense if that scaling came from a quantum gravitational effect. Like this is where it came from. So because that's basically what we're looking for, right? We're looking for some kind of connection between the observation that we have of the cosmos out there and some deeper underlying theory. So MOND is, to pick up on what you said earlier, it's a phenomenological model. It was built to describe correlations that we see out there. So those are there. And the model fits the correlations, not all of them, unfortunately. So this is the entire problem with MOND. Not everything wants to fit. But this scale, like with the cosmological constant, or I forget, maybe it was the cosmological constant divided by 3 or something like that. It just falls out of the data. And so I find this like super perplexing. Like, why? Like, why does it have something to do with the cosmological constant? It just, it seems to indicate to me like we're missing something. Like there's something else going on that we don't know. And so this is why I found this paper interesting. So as I said, it's not a new model of quantum gravity. You still need some assumptions about what the quantum fluctuations of space-time are that ideally have to come from an underlying theory. But what they provide is this connection between the underlying quantum gravity, the fluctuations of space-time and so on, and something that we can actually observe. So that's why I thought it was interesting.
And that's why it's interesting, because the problem with quantum gravity is that it generally, as interesting as it might be theoretically in terms of observations, it's often, so far completely inaccessible. And so the holy grail for years and years is to find some effect that would allow us to test something about the quantum mechanical nature of gravity. We've, as you know, I've argued that in gravitational waves, you might be able to do that at some level, and so that's the point of this paper, is that anytime you find a prediction that might be observable, it's worth exploring. The question, of course, as you say, is whether this calculation which is an approximation, is right. In the press release, are there other people in that field who comment on that and are skeptical or not? Do you know?
Not yet.
Not yet.
I mean, me, right? So I just commented on it, and I'm skeptical.
Yeah, you just commented.
But the press release is just the authors of the paper.
Oh, just the authors of the paper. Okay.
Yeah. So it comes from the university.
If it is observable, I find it suspicious. I mean, when I read about it, I didn't look at the paper, but I found that fact suspicious. But we'll see. I guess I'm also not too surprised when scales coincide. After all, the cosmological constant, the dark energy, as we would call it, basically is a scale that's comparable to the size of the universe if you look at a physical scale. So it's not too surprising that if you look at other effects that might be relevant on that scale, they're related, because it's like the Hubble constant. There's one fundamental scale that determines more or less the age and size of the universe, and everything. It's not too surprising that other things that happen cosmologically are related to that scale. So it's so important. It might just be, an accident when you try and fit things, you come up with that scale. But it'll be interesting to see. I do know for a while there were, and this is probably not related, but there were claims that quantum foam would also change the trajectory of high energy cosmic rays, and you could somehow, see high energy cosmic rays scattering off quantum foam and quantum gravity in an observable way. But as far as I know, any such claims have later on been shown not to be the case, or at least not to be observably important that so far. So it'll be interesting to see. Certainly, it would be profoundly important if any quantum gravitational effect were actually observable. And so I do applaud people looking for just that, because it's really the only way we'll know if we make any progress, I think, in that area, in fact.
Totally.
To go from that extreme of theoretical speculation and high energy physics back to the world that relates to us, I want to do one real discovery that is fascinating, that comes from not astrophysics, but planetary science, and it is the recovery of material from the asteroid Bennu. That was, I think, a Japanese experiment, and well, the Japanese are looking at it. It's the OSIRIS-REx experiment that still amazed me, that got material and brought it back for us to study on Earth. And not surprisingly, we're surprised. And it's actually of quite great interest to me that there's already, anytime you've looked at asteroids or comets, one of the big surprises from years and years ago is that there's complicated organic materials that are created in space, which is very exciting if you want to think about the origin of life. So the phosphates, bases of DNA and amino acids, all of those have been observed in comets and such. But what's really interesting in this case is that, so all of the 5 phosphate bases, all of the bases of DNA have been seen, but DNA is called deoxyribonucleic acid, and RNA is ribonucleic acid, because the ribo comes from a sugar called ribose, a 5-carbon sugar, and glucose is a 6-carbon sugar. And what has been seen on the asteroid is ribose for the first time, which is basically the other building block of RNA. You've got the phosphates, and then you have this ribose. And what's also extremely interesting is that they don't see deoxyribose, okay, which is the bait, which would be necessary for DNA. And so now every single component for what we call an RNA world in the early Earth, many people think that the first forms of life happened not based on DNA, but based on RNA. And it's a simpler way to do things, and it could have been a precursor. It's an interesting idea. But now what's been seen is, in fact, every component for an RNA world now has been seen to be available in the interstellar medium to come to Earth on this asteroid, and the deoxygenated part of it, the deoxyribose, hasn't. So it is suggestive that indeed an RNA world might be the way things began. But it's just amazing that all these things exist out there, and the clue to why we're here may be, once again, looking outside. Not that we're created by alien species by any kind of panspermia, but it could be that simple simple chemistry, and there's lots of chemistry that goes on in space, which is, again, I think, initial surprise. On the surface of ice comets or rocks, there's energy, there's cosmic rays, there's lots of energy available to do chemistry, and it all seems to be happening. And I think that's interesting. Not just that, but there's a kind of gum that was observed that's never been seen, a kind of sticky material, a polymer. So complicated polymer creation of really complicated long organic molecules is happening in space, and that's highly suggestive that the Earth maybe had gotten a jump start, and we didn't need really exotic processes on Earth to create the building blocks of life. And so I find it fascinating. Any comments?
I find this interesting for 2 different reasons. One is that we can kind of see how the opinion of scientists about the origin of life changes because of this data that we're gathering. So this is like, I mean, correct me if I'm wrong, but I think this is a fairly recent thing. As you say, like, this is like really surprising that we're discovering more and more complex molecules out there in asteroids, in also in samples from Mars. I think we talked about this recently. And with spectroscopic analysis, what's going on in molecular clouds and this kind of stuff. It all builds up to much more complex chemistry than anyone expected. So, so this is the one reason I think it's cool, because we're learning something new, like which comes from the data, like it's data driven, and it's happening as we speak. And the other thing is, of course, what does it mean about life on other planets? And I think what it tells us, like, for one thing, it might be much easier to create life than we thought it was, because the first ingredients could come from outer space. And the other thing I think that it tells us is that if there's life elsewhere, it's likely to have similarities to us, at least in this chemical basis that it's built on. It's probably not something completely different.
It's not like the Horta in Star Trek. It's not made of rocks. I want to pick up on both those things. I think it's incredibly important. It reminds me, it goes back when I was a kid. I learned of the Urey Miller experiment. You may remember the famous experiment where they basically put what they thought was the early atmosphere of the Earth in a flask and put lightning through it, namely sparks, and they discovered all this goo, all this organic goo. And they said, "Oh, great! Now we can see in the early Earth. This is maybe how organic materials are created." The problem was, it turns out the atmosphere they used wasn't the atmosphere of the early Earth, and now we've learned that you don't even need that. That you get this jump start, which I think is fascinating. As you say, and for me, it means that you're absolutely right. That I think I'm personally convinced that life is ubiquitous. I don't mean intelligent life, but organic material based life. And I have an ongoing bet, which I don't expect to ever win or lose in my lifetime, but we'll see, with people like Richard Dawkins, that the more I've studied ideas of the origins of life, the more I'm convinced that life has found the only mechanism that really works. And I am convinced that if we find extraterrestrial life, it'll not only be similar, but it'll be more or less identical. It'll be based on the same base pairs of DNA and ATP as a power producing molecule. I think life, by exploring all of the phase space of chemistry, quite likely found the way that works. And the example of that is that we don't see any other kind of life on Earth. It's all based on the same kind of chemistry. So I'd love to be wrong. I'd love to see some weird form of alien life. I wouldn't be surprised if under the oceans of Europa, if we first discover molecular life, small scale living things, that they look identical, and we'll see. But that's the great thing. We'll see, because all of this will be looked at, and it may be surprising, because every time we look out there, we're surprised. So we got to keep looking. And I think that's a good way to sum up this always incredibly enjoyable chance to chat with you about what's interesting or maybe not interesting in science this month. And happy birthday to your friend who had the same birthday as you. And I look forward to talking to you next month. Thanks, Sabine.
Next year.
Next year. You're right.
Yeah.
Next year. Okay. My goodness. Okay. You take care. Bye-bye.
Bye.
Hi, it's Lawrence again. As the Origins podcast continues to reach millions of people around the world, I just wanted to say thank you. It's because of your support, whether you listen or watch, that we're able to help enrich the perspective of listeners by providing access to the people and ideas that are changing our understanding of ourselves and our world and driving the future of our society in the 21st century. If you enjoyed today's conversation, please consider leaving a review on Apple Podcasts or Spotify. You can also leave us private feedback on our website if you'd like to see any parts of the podcast improved. Finally, if you'd like to access ad-free and bonus content, become a paid subscriber at originsproject.org. This podcast is produced by the Origins Project Foundation as a non-profit effort committed to enhancing public literacy and engagement with the world by connecting science and culture.